Here we have a power series. In this video, we're going to look at determining the interval of convergence as well as the radius for that interval. And then we're asked, at what values of x does the series converge absolutely? And also, for what values of x does the series converge conditionally? The first thing we're going to do here is apply the ratio test. And what the ratio test says that we're going to take the limit as n goes to infinity of the absolute value of u sub n plus 1 over u sub n. And by the ratio test, if this value is less than or equal to 1, then we will have absolute convergence. So let's set that up. We're going to have the limit as n goes to infinity of 3x minus 2 to the n plus 1 power over n plus 1, all of which is divided by 3x minus 2 to the n over n. So let me simplify what I have in here using a little bit of algebra, copy, change, flip. I now have the limit as n goes to infinity of the absolute value of n times 3x minus 2 over n plus 1. So this value, we want this limit to be less than 1. And as long as it's less than 1, we'll be able to determine absolute convergence. So what I'm going to do, since we're not dealing with any x's in our limit, is I'm going to pull that 3x minus 2 out in front. I'll leave absolute value bars around it. So the absolute value of 3x minus 2, and then we have times the limit as n goes to infinity of n over n plus 1. We want this to be less than 1. The limit of this we can find using L'Hopital's rule because it's already in the indeterminate form of infinity over infinity. So the derivative of the numerator is 1, the derivative of the denominator is 1, and the limit as n goes to infinity of 1 is just going to be 1. So we're left with 3x minus 2. The absolute value of that needs to be less than 1. By using our absolute value property of equality, I can create this statement here in conjunction. I'll add 2 to both sides. That gives me positive 1 less than 3x less than 3, and divide by 3 on each of these sides. And I have 1/3 less than x less than 1. So we know that this is the interval where my series is absolutely convergent. So if it's absolutely convergent on this interval, we know outside that interval it would be divergent. So what we could say is it is divergent for any x value that is less than 1/3 or any x value greater than 1. And these two values would just have been found by solving this inequality, this absolute value inequality, with a greater than 1. Because by the ratio test, if that ratio is greater, or essentially your rho value is greater than 1, that means it's divergent. However, at the values where it is equal to 1, which would occur at x equals 1/3 and x equals 1, this is inconclusive. Therefore, we have to look at both of the conditions on either of those endpoints. So we found A, an interval where we are absolutely convergent. We have found B, intervals where this is a divergent series for any x value less than 1/3 and any x value greater than 1. But we also have to look at those endpoints, which would be the x values that make this equal to 1. And that's where our ratio test doesn't tell us any specific information. So the third thing I will look at is we'll say, well, let's look at x equals 1. What does that do to our series? So my series was n equals 1 to infinity of 3x minus 2 to the n over 1. If I plug x equals 1 in here, that's going to give me this expression, 3 take away 2, I'll have 1 to the n. So this is the sum as n equals 1 to infinity of 1 to the n over n. And 1 to the n in the numerator, that's just equal to 1. So now this is the sum of a harmonic series. And because this is harmonic, it diverges at x equals positive 1. So we look at one last piece here, and that would be at x equals 1/3. So what does that give me for my sum from n equals 1 to infinity? Plugging in 1/3 for x, 3 times 1/3 is 1. 1 take away 2. This gives me negative 1 to the n over n. And essentially here, this means we're finding the sum of negative 1 to the n times 1 over n, and that is an alternating harmonic series. And if you have an alternating harmonic series, we know that that is convergent. So this converges at x equals 1/3. Right, so now I'm going to go and summarize all of that on one screen. Therefore, we have made all the following conclusions. This given power series was absolutely convergent by the ratio test for x values between 1/3 and 1. And it was divergent for x values less than 1/3, as well as x values greater than or equal, because at x equals 1, it was divergent. So it's not absolutely convergent everywhere. It is conditionally convergent, and we can include that x equals 1/3. So we have this conditional convergence, and that leads us to our interval of convergence. And the interval of convergence is everywhere that it is converging. So inclusive of the 1/3, but less than 1. And the radius is just going to be the difference of these two values subtracted and then divided in half. So my radius would be 1/3 minus 1, all of that divided by 2. The difference of those is 2/3 divided by 2. We have our radius is 1/3. And another way to think about that is if we had 1/3 and 1, and we went to that center point, would be 2/3. The radius is that distance from the center to either end. So that's a 1/3 of a unit there. So I hope that helps you kind of understand the difference between absolutely convergent and conditionally convergent. As always, get in touch with me, email me if you have any questions.